Okay, so here's our question. Jeffrey Jones rode 18 miles down the Delaware River in 2 hours, but the return trip took him 4.5 hours. Find the rate Jeffrey can row in still water and find the rate of the current. Hint, distance equals rate times time. So if you notice in this table, they already gave me a table which is missing the distance and the time, but the rate is given to be x plus y for downstream and x minus y for upstream. What they did not mention is that x will represent the rowing speed of Jeffrey in still water, and y will represent the current speed. So I did make note of that to the side. Okay, so now let's fill in our table, first filling in the distance. And the distance from the problem is given to be 18 miles. So he's going to go 18 miles downstream, and then he's going to go back to where he came from, and he's going to go 18 miles upstream. Okay? And now the time. Filling in the time, I'll notice there are actually 2 times given. Okay? 2 hours and 4.5 hours, which I will actually represent as 4.5 hours. Be a little easier to work with. Now I gotta figure out which one would be 2 hours and which one would be 4.5 hours. So let's focus on the downstream. If I look at the rate of the downstream, it is x plus y, which means that you're adding the current speed to Jeffrey's rowing speed. So the current is helping him, allowing him to go faster than he would be going on his own. The faster you go, the less time it takes to get somewhere. So the 2 hours would go here. Similarly, at the upstream, we're subtracting the current speed from the rowing speed. It's x minus y. So if we're going to go slower, it's going to take us longer. So the 4.5 hours will go there. Take a second to make sure you understand why the 2 is where it is and why the 4.5 is where it is. Now continuing this problem. The hint is that distance equals the rate times the time. So using this in my table, my first equation for my system, my first of my 2 equations, will be 18 equals the rate, which is x plus y, times the time, which is 2. And my second equation of my system will be 18 equals x minus y times 4.5. Okay, so those are my 2 equations that I've set up for my system, and that's, again, the key to these problems is setting up these equations. Okay, there's a couple routes I could go to solve this problem. One thing that is taken advantage of is I can divide both sides of this equation by 2, and I can divide both sides of this equation by 4.5. And if I do that, 18 divided by 2 is 9. And here the 2's would reduce to 1 over 1, and I would just get x plus y. Similarly in the bottom, 18 divided by 4.5 is 4. And here similarly this will reduce to 1 over 1, so I'll just get x minus y. Alright, so now I have these 2 equations. Looking at these 2 equations, they set up very well for the addition method. They also set up for substitution, but addition will be a little bit quicker. So using the addition method, 9 plus 4 is 13. X plus x is 2x. Positive y plus negative y will eliminate. I get 13 equals 2x. Divide both sides by 2. And I will get 6.5 is x, or 6.5 is x. And remember, x represented his rowing speed in still water. Okay. And now I need to find y. So finding y, I will go back to one of my equations. I could go back to my original equations, or I could go back to some of my new equations I've set up. I'm actually going to go back to this equation. Okay, 9 equals x plus y. It looks to be the easiest of all the equations. So I'm going to jot that equation back down. I know that x is 6.5, so I will substitute that in. I'm going to take away 6.5 from both sides to get y by itself, and I will get 2.5 equals y. So it appears that the rowing speed in still water, which is x, is 6.5, and the current speed is 2.5. If I look at my units, it's miles an hour, so it's 6.5 miles per hour in terms of Jeffrey's rowing speed, and it's 2.5 miles per hour in terms of the current speed. Okay, hope this helps.